Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1984 Nobel Prize lecture delivered by Subrahmanyan Chandrasekhar, formerly titled On Stars, Their Evolution and Their Stability, stands as a remarkable document in the history of science. It functions as a capstone intellectual autobiography, a rigorous defense of mathematical physics, and a profound meditation on the nature of scientific discovery. To engage with this work is to engage with the mind of a scientist recounting the genesis of a concept that redefined our cosmic landscape. This essay undertakes a deep, section-by-section evaluation of the internal claims, logical progression, and conceptual frameworks presented within that lecture. Its purpose is to analyze the cogency of Chandrasekhar's arguments, as he himself chose to articulate them a half-century after his foundational insights. The lecture's narrative unfolds with a deliberate, almost classical, sense of order, moving from established 19th century principles to the revolutionary implications of his own work. We will follow this intellectual path, assessing the strength of each link in the logical chain he so carefully forged for his Stockholm audience and for posterity. This analysis will illuminate how Chandrasekhar constructs his case, presenting his discovery of the limiting mass for white dwarf stars as the inexorable outcome of applying the known laws of physics with unflinching consistency. Section 1. The classical framework of stellar equilibrium. Chandrasekhar commences his lecture by establishing the intellectual bedrock upon which his own contributions were built. He presents a specific claim regarding the state of stellar physics in the early 20th century, that the theory of polytropic gas spheres, pioneered by figures like Lane, Ritter, and most comprehensively by Robert Imben, provided a mathematically complete and internally consistent model for stellar structure. His evaluation of this older framework is generous, portraying it as an elegant and powerful tool of classical physics. He meticulously details the core mechanism of this model, the Lane-Imben equation, which describes a sphere of gas in hydrostatic equilibrium under its own gravity, governed by a simplified equation of state, where pressure is proportional to density raised to a constant power. The internal logic he presents is compelling. He demonstrates that for a given polytropic index, the equation yields a unique solution for the star's structure, allowing astrophysicists to model stellar interiors with surprising accuracy using only classical mechanics and thermodynamics. The evaluation of this claim must affirm its historical and pedagogical validity. Chandrasekhar's portrayal of the polytropic model as a self-contained and successful theory for its era is entirely accurate. He correctly identifies its power in its ability to circumvent the complex details of energy generation and transport, offering a global solution for a star's mechanical balance. His argument here serves a crucial rhetorical purpose by lauding the completeness of the classical picture. He sets the stage for the crisis that would necessitate a new, quantum mechanical intervention. He presents it almost as a finished piece of architecture, beautiful and symmetrical, yet ultimately incapable of housing the strange new realities that observational astronomy was beginning to reveal in the form of white dwarfs. Section 2. The introduction of degenerate matter and Fowler's contribution. The lecture's second major movement pivots to the first application of quantum theory to the stellar problem. Here, Chandrasekhar advances the claim that R.H. Fowler's 1926 insight, applying the newly formulated Fermi-Dirac statistics to the matter within white dwarfs, constituted the essential conceptual leap that explained their paradoxical stability. He explains Fowler's core argument with precision. The electrons within these incredibly dense stars are forced into a state of quantum degeneracy. According to the Pauli exclusion principle, these electrons must occupy a vast range of momentum states, creating an immense pressure that is a function of density alone, almost entirely independent of the star's temperature. Chandrasekhar's claim is that this degeneracy pressure was the missing physical mechanism. The evaluation of this assertion finds it fundamentally sound. He correctly identifies Fowler's work as the solution to the puzzle of how a star like Sirius B could be as massive as the Sun, as hot as a blue giant on its surface, yet as small as the Earth without collapsing. A classical gas would lack the pressure to support such an object once it cooled. He explains that Fowler's model, by making pressure a consequence of density, effectively rendered a white dwarf a specific type of polytrope, one with an index of 1.5 for the non-relativistic case. In his lecture, Chandrasekhar frames Fowler's contribution as a triumphant resolution, and this is a valid assessment of its immediate impact. It provided a robust physical basis for the existence of white dwarfs using the most advanced physics of the day. Yet, in his careful telling, a subtle intellectual tension is preserved. He presents Fowler's work as the definitive answer for the white dwarfs then known, while implicitly noting the physical domain it left uncharted, the realm of relativistic speeds, which electrons in even more massive and compact configurations would inevitably reach. Section 3. The synthesis of special relativity and the emergence of the limit. This section of the lecture constitutes its intellectual and emotional core. It is here that Chandrasekhar details his own unique and transformative contribution. His central claim is that the consistent application of special relativity to the equation of state for a degenerate electron gas leads to the unavoidable conclusion that there exists an absolute maximum mass for a stable white dwarf star. He meticulously reconstructs the logical path he followed as a young man aboard the ship to England. He explains that as a star's core contracts and its density increases, the degenerate electrons are forced into higher and higher energy states, their velocities approach the speed of light, and relativistic effects become significant. The critical step in his argument, as he presents it, is the change this induces in the relationship between pressure and density. In fully relativistic limit, the equation of state alters its character, approaching that of a polytrope with an index of 3. This is the argument's fulcrum. Chandrasekhar then invokes a known, purely mathematical result from the study of polytropes. A star modelled by a polytropic index of 3 has a mass that is uniquely determined by the underlying physical constants, independent of its central density. The evaluation of this claim reveals its mathematical and physical inevitability. The logic is a masterpiece of physical deduction. By combining quantum statistics with special relativity, he demonstrated that a star's ability to generate pressure reaches a finite ceiling as more mass is added. The inward pull of gravity, which scales with mass squared, will always overwhelm the outward push of relativistic degeneracy pressure, which scales with a lower power of mass. He presents the equation for this limiting mass, a beautiful and profound formula. In spoken form, the limiting mass is shown to be a value on the order of 5.76 divided by the square of the mean molecular weight per electron, all multiplied by the mass of the Sun. He derives this value from fundamental constants in numerical factor, approximately 0.197, multiplied by a combination of Planck's constant times the speed of light, all divided by the gravitational constant. This entire quantity, raised to the power of 3/2, and the result divided by the mass of a proton. The argument, as presented in the lecture, is unassailable. It flows directly from the premises of established physics. Its strength lies in its purity. There are no adjustable parameters, no appeals to unknown physics. It is a direct mathematical consequence, and Chandrasekhar's presentation emphasizes this quality of stark inevitability. Section 4. A reflection on the Cambridge confrontation. In a section of remarkable candour, Chandrasekhar addresses the famous and painful controversy with Sir Arthur Eddington that followed the announcement of his discovery. His core claim here is an assessment of the nature of their disagreement. He posits that the conflict was fundamentally a clash between two irreconcilable conceptions of how science should be done. His own approach, he argues, was one of rigorous mathematical deduction from established physical laws, following the logic wherever it might lead. Eddington's approach, in contrast, was rooted in a deep-seated physical intuition and a philosophical belief that nature would preclude the kind of stellar catastrophe his theory implied. Chandrasekhar recounts Eddington's public ridicule, quoting his assertion that the star has to go on radiating and contracting until, I suppose, it gets down to a few km radius, when gravity becomes strong enough to hold in the radiation, and the star can at last find peace, the evaluation of Chandrasekhar's claim about the nature of the dispute supports his interpretation. He presents Eddington's objection as lacking a specific physical or mathematical counter-argument. Instead, Eddington's critique was an aesthetic or philosophical one, an appeal against a conclusion he found absurd. With a touch of historical irony that is almost palpable in the text of the lecture, Chandrasekhar highlights that Eddington's own off-the-cuff description of a star trapping its own radiation was, in fact, a startlingly accurate, if accidental, description of a black hole. This section is a powerful defense of the primacy of mathematical consistency over received wisdom, or even the intuition of a giant like Eddington. Chandrasekhar's framing is, of course, that of the vindicated party. Yet the evidence he presents for the philosophical, rather than scientific, basis of Eddington's objection is persuasive. The claim is that the argument was about methodology and scientific taste, and this assessment has been largely borne out by historical analysis of the episode. He successfully portrays the confrontation as a pivotal moment, a test of the scientific community's willingness to accept a deeply counterintuitive but mathematically sound prediction. Section 5, the astrophysical consequences, and a new cosmic landscape. In the concluding scientific segment of his lecture, Chandrasekhar articulates his work's ultimate claim to significance that the existence of the mass limit for white dwarfs fundamentally reshapes the entire narrative of stellar evolution and necessitates the existence of other, more exotic stellar endpoints. He argues that the limit is a cosmic fork in the road. For stars with core masses below about 1.4 solar masses, the destiny is to become a stable white dwarf, slowly fading into obscurity. For any star exceeding this mass, however, this peaceful end is unavailable. The implication, he states, is that nature must have another path. This claim is an evaluation of his own work's predictive power. He masterfully connects his calculations from the early 1950s to the subsequent theoretical work on neutron stars by Oppenheimer and Volkoff, and ultimately to the concept of the black hole, the final victory of gravity. The evaluation of this claim is unreservedly positive. The Chandrasekhar limit is precisely the gateway to the entire field of compact object astrophysics. His lecture correctly positions his discovery as the theoretical prerequisite for understanding phenomena like supernova, pulsars, and quasars. He demonstrates that his limit is a demarcation line separating the realm of familiar stellar physics from a new, more extreme physics where general relativity and nuclear forces dominate. The claim is that his calculation opened a Pandora's box of astrophysical possibilities, and the subsequent history of the field has proven his assertion to be entirely correct. He presents his limit as a question to the universe, and he alludes to the answers that a later generation of scientists, armed with new theories and observational tools, would provide. In conclusion, Subrahmanyan Chandrasekhar's 1984 Nobel lecture is a document of extraordinary intellectual coherence and persuasive power. A close, internal evaluation of its claims, section by section, reveals a meticulously constructed argument that is as logically sound as it is historically compelling. From his respectful establishment of the classical polytropic framework to his lucid explanation of Fowler's quantum mechanical insight, he builds his case with the precision of a master craftsman. The central claim of the lecture, that the union of special relativity and quantum statistics mandates a maximum mass for white dwarfs, is presented as a deductive certainty, a truth that emerges directly from the laws of nature. His candid reflection on the Eddington controversy serves to champion a scientific methodology grounded in mathematical rigor against one based on intuition, a principle that his life's work came to embody. Ultimately, his assertion that the limit's existence opened the door to the modern universe of neutron stars and black holes is a statement of his own profound and enduring legacy. The lecture stands as a testament to a discovery that was at once a mathematical certainty, a philosophical challenge, and the beginning of a profound revolution in our understanding of the cosmos. It validates a vision of science where the relentless pursuit of logical consistency can unveil truths far stranger and more wonderful than imagination alone could conceive.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.